This screencast is an overview of the use of the Peng-Robinson property calculator in Matlab. The code that runs the graphical user interface is called PreosPropsMenu. The code that actually does the workhorse calculations is called PreosProps. This screencast assumes that you already understand how the Matlab folders are structured. We've covered that in other screencasts, and how the Matlab props folders are used to hold properties. It also assumes that you have worked with the Peng-Robinson equation of state for PVT properties as a precursor. It assumes that you have studied chapters 7 and 8 and understand the concept of use of departure functions for calculating properties. I'm going to start this screencast by discussing the function statement and then discuss the GUI and get into the calculations. Alright, so if we go to the ChemiThermo folder, you can see I put the programs here in ChemiThermo. I'm going to go into the Matlab folder, and we're interested in the property calculations in chapters 8 and 9. And I'm going to first open PreosProps. There are 3 files here that are Matlab files. PreosProps, which will do the property calculations, PreosPropsMenu.fig, which is a graphical figure file that does no computations itself. It simply serves as the graphical user interface. PreosPropsMenu is the Matlab code that interacts with the graphical user interface to collect information, pass it to PreosProps, and then the results are passed back to the graphical user interface. So let's look at PreosProps. Let's look at the function statement here. And you can see that information returned from the program includes the compressibility factors, the enthalpy values, entropy values, internal energies, fugacities, and a vector info that has information about the convergence of the particular routine that was used. PreosProps is the name of the code. It requires input that we will provide on the graphical user interface, including a reference temperature, reference pressure, a temperature and pressure of interest, and we will also construct information to create this vector match, which specifies if matches are to be done, which properties are to be matched, and which values are to be matched. Okay, so now let's open up the GUI and take a look at the GUI. To load the GUI, I'm going to use run PreosPropsMenu. I'm using tab completion. And I get the GUI interface. You can see that as it loaded, it is operating with propane, and a default reference temperature and pressure are loaded. This is the temperature and pressure of interest. The box run type specifies what type of run is to be done. The default is to do no matching and simply use the specified temperature and pressure and calculate the properties. When that is done, in the result box, we can see at a temperature of 298.15 Kelvin and 0.1 megapascal, propane is found to have 3 real roots, and 2 of them are kept. One is a vapor-like value, Z equal 0.98. The other is a liquid. And here are the corresponding volumes, internal energies, and so forth. Okay, the lowest fugacity root is stable, and therefore the vapor root is stable. We are going to be working with carbon dioxide, so we're going to want to set the props row value. Alright, I've predetermined that the property row number to use is row 62, and I'm going to search for props row in the code. And I need to set this to 62 for properties of carbon dioxide. Control S to save that. I can redock it. Okay. And now I can run props menu again. Okay, now you can see that I've got carbon dioxide, and I can begin to enter temperatures and conditions. Now my first objective is to find conditions at 213 Kelvin and 1.5 megapascal. Okay, so I'm going to set the temperature to 213, the pressure to 1.5. I do no matching. I just click calculate. You can see that 3 real roots are found. Of the 2 roots, the lower fugacity is the liquid-like root with a volume of about 35.2 cubic centimeters per mole. That is the more stable root. Alright, next let me find saturation temperature at a pressure of 0.5 megapascal. So I'll go back to here, and I want to choose a pressure of 0.5 megapascal. And at first I'm just going to press calculate. I always want to start with an initial guess. Alright, and you can see that I put in 213 Kelvin and 0.5 megapascal, and I can see that I've got a condition where the 2 fugacities are not too far from each other. You always want to do trial and error to get close before you try to use solver. In this case, I'm close. I can try to find saturation. It will adjust to make the fugacities equal. It doesn't matter what root I'm using. I'm going to adjust temperature, and value to match is not important. Okay, and now if you look at the fugacity values, you can see that they have been matched. The temperature is found to be 216 Kelvin, so this is the saturation temperature for carbon dioxide at 0.5 megapascal. And you can read corresponding saturation vapor values and saturated liquid values. If you need to do a quality calculation using the Peng-Robinson equation of state, this is the way you would generate the saturation conditions. I can do an analogous type of calculation if I set the temperature and look for the vapor pressure. Now let me look for an entropy value of minus 20 at a pressure of 0.5 megapascal. Alright, first I'm going to look to see how close I am. I'm looking for an entropy value of minus 20, and I'm going to find that with a vapor root. You can see the value currently is minus 25, so it's not too far away. So I can choose to match a certain value of S. I'm going to use it by matching the large compressibility factor root. I'm going to adjust temperature, and the value I want to match is minus 20. Alright, and I press calculate, and you always want to make sure it worked. In this case it did. The value is found. Now once the value is found, before you accept the values, you also want to make sure that the root that is found that you searched for is the stable root. In this case it is, because the fugacity is lower than the value of the fugacity for the liquid root. Let's do a more advanced calculation where we want to find internal energy and volume by adjusting temperature and pressure. We've written a customizable user objective function where you can set the properties that you would like to match. So if I go back to the code, to save time I know where to look for it. Okay, I'm going to search for the function called user obj, and I'm looking for the function that has that name. Alright, so here I found the function. Alright, it has input of the reference temperature and pressure, a vector TNP, and match. And if you look, T and P is a vector that holds temperature and pressure, and I simply unpack it first. I then calculate the properties using the temperature and pressure and reference conditions, and then match is used to decide which root to keep, in this case the value of match element number 4. Okay. And then here is where the user objective is used. All right. There are different formats here. If you read the comments, depending on the solver that you use, you can turn on and off certain comments. All right. Now, if you look for a moment here in the commented lines, I've got an equation that would optimize for a volume of 88.46. ZRT over P would be volume. When that divided by 80.46 goes to 1, this objective function is matched. When U goes to minus 5330, the second objective is matched. Well, I can use those and adapt them for my particular application. Okay, I've copied and pasted those two objective functions. Notice that I've changed the volume to be 5,000 and the internal energy to be minus 3,000. All right, I can then save this, and I can return to my GUI. And I usually want to make some initial guesses, looking for a U value minus 3,000, near minus 3,000, and a V value that's near 5,000. In this case, I chose conditions that are pretty close to where I left off. So I don't need to change my initial guess. All right, so let me just calculate. Okay, and you can see I've matched the volume and I've matched the internal energy. Okay, so we've accomplished our objectives. I do want to make a very important point about reviewing the command window. You always want to look at the command window after a convergence is done. You can see that there's information here about the objective function and how it was met. In addition, you see a note about manually change the value of T and P in the workspace. This is so that the program doesn't automatically overwrite values in case a convergence fails. This then prevents it from writing bad values to the workspace. So instead, the original values are there until you change them as the user. All right, also notice that we've got departure information that is shown to the command window, not to the GUI. Finally, notice that there is a bug that sometimes after using the solver you have to reset the adjust T or P to re-register that. Okay, thank you.